Good morning, friends. Welcome to this session on dynamics of machines. In particular, we are going to talk about balancing of rotating and reciprocating machines. So, we are going to have three sessions. Today is the first of it, and today our concern will predominantly be on rotating machines. So, to carry on, the outline of the talk is as follows. So, firstly, I will take some time to introduce the concept of dynamics of machines. What are the important things concerning the dynamics of machine regarding the forces that are generated in machines, and in the better part of the time that is available today, we are going to talk about balancing of rotating machines. So that is going to be our focus for the day. Tomorrow when we come back, we are going to talk about balancing of reciprocating motions, that will spill over even to the third day, and hopefully we should have some problem solving sessions also. So with that in mind, let us make a start. So I will invite you to this world of machines. Machines, as you know, is all about different moving parts. So here in this talk I am going to concentrate about two specific classes of machines, one rotating machines and the other which are having reciprocating parts. So as an example of machines which are only rotating parts, you could see this machine, it is a turbo machine. Likely it has been taken from Google Images, so I do not know much details about this machine other than the fact that it looks like a turbo machine. So what is very important for this machine is that these rows of blades that you are seeing here, all of these will rotate, right. So this is a rotating machinery, and in this turbo machinery we do not get to see any reciprocating part. Contrast that with the figure on the right. This is a sketch of an internal combustion engine typically used in a automotive setting. So in an internal combustion engine, you will have the crank which is rotating at some speed, and you will have the piston which is accordingly reciprocating. So internal combustion engines will be an example of those class of machines which have both rotating as well as reciprocating parts, and turbo machinery will be an example of those machines which have only rotating parts. So as I said, today we are going to deal with machines which have only rotating components, and tomorrow when we come back we are going to deal with machines which have rotating as well as reciprocating components. So there is scarcely any machine which does not have any moving parts whatsoever. So all machines will have moving parts. Obviously there are more complicated machines which will have special kind of motion like robots and whatnot, but that is scope of the present discussion. What we need to do, what we need to discuss about in this period of 6 hours is rotating motion and reciprocating motion. So with that in mind, let us go forward. So the point is, these moving parts, whether you look at these turbo machinery blades or whether you look at the crank, piston and connecting rod, all of them need to be connected to the static part of that machine, and in kinematics or in mechanics we refer to the static part as the frame, right. So when you do a kinematic diagram, you always intend to show the frame as, let us say, link number 1, and the motion of all moving parts is with reference to this frame. So it is very important to understand that the moving parts are not hanging in thin air, but the moving parts are connected to some part which is not moving, which is the static part, and that part in the generalized sense defined as frame, and each moving part is connected to another part by some revolute or sliding pairs. So when you have a rotating machinery of this sort, you just have one moving part which is this rotating shaft, and this rotating shaft gets connected to the frame through some bearing, as will be shown in the next slide. So this is a rotating machinery, not probably the same. Again, this has been taken from Google Images. So you see a rotating machinery, and this rotating machinery is connected to the static part. So this cylinder is going to rotate about what? Rotate about the stationary part, right. So this stationary part will be referred to as the frame of the analysis. The frame is one typical link which is going to be the static link, and the motion will be with reference to this body. So that is the frame for you. So let us first understand when the machine is not switched on, when the machine is actually not operating, it is not even powered. So in that case what happens? So this is the machine for us. It's supposed to be a portable lathe cutting machine, portable lathe machine. That's what at least the Google image says. So none the same for us. All that is important to understand is that it's a rotating machine. So if you consider a schematic of this rotating machinery, so this is the rotating machinery. I just show that through blue blocks. I don't know what are there inside these machines. It could be a turbo machine, it could be something else, but doesn't matter for the present analysis. So this rotating machine shown by this blue patch is mounted on a shaft which you see is drawn as this black line. So this entire body, the black line together with this blue cylinder, is going to undergo rotational motion, and it is going to rotate about the frame, right. So the connection, the interconnection between this rotating shaft and the static frame is through this bearing. So bearings are usually drawn in this fashion, though I will possibly be not this perfect in my later drawings, but this is how bearings are supposed to be drawn. On one side of the bearing you have a connection with the static part, and on the other side of the bearing you have the connection to the rotating shaft. So the shaft is going to rotate within its bearing, and the bearing on its other side will be connecting towards the frame. Now let us take a free body diagram between these two components, first the rotor shaft system and second the frame. So on the rotor shaft system, the entire forces that are acting on the body, remember we are now talking about a machine which has not even started. So to balance the weight of the machine, there has got to be forces from the bearing onto the shaft. These are indicated by the red arrows, right. But now because there are forces which are acting on the rotor shaft system from the bearing, there has got to be a reaction which are indicated by the green, right. So what I intend to show you through this schematic is that for any machine, even if it has not started operating and therefore there are no moving parts, there has got to be an interaction of forces between the frame and the moving parts of the machine. In this case the moving parts have not even started moving, that is beside the point, but there are forces, and these forces are always coming in action reaction pair. So whenever, so I will make some notes at this point. The important point at this stage is to make a remark that machines have moving parts, and we are going to study machines with two types of moving parts, namely rotating and reciprocating. We are not going to study machines having a complicated spatial motion, which is typically true for robotics, but for this course that is outside this present scope. And these moving parts are connected to the frame but there is always an interaction of force between the machine and the frame. And as per the example that is shown, if I have to draw that again, so this is my rotor shaft system. Obviously the rotor has some force, so this is the weight which is equals to mg of this component. To balance this weight, the bearing has to put in certain reactions, and let us say it is a symmetrically arranged, so therefore the bearing has to put in an amount of force which is W by 2 and W by 2 at both the ends. So therefore from the perspective of this rotor shaft system, you get to see that it is being acted by three forces, namely the gravitational force, but to ensure that the machine component is held in the static equilibrium position, the bearings will have to supply equal and opposite forces so that both the moments as well as the forces balance. But now because there is a force which is coming from the bearing to the rotating part, there has got to be a reaction force which goes as an action reaction pair from the rotating part to the bearing, and this will act on the frame, right. This is exactly what I had drawn in my slide. So here this is the free body diagram. The red arrows indicate the forces acting on the machine, and the green arrows represent the action reaction pair. Because there is some force acting on the machine, there is a reaction force which is coming from the machine to the ground or the frame. So these two are the free body diagrams. So even in the case that the machine is not operating and it is just in a static equilibrium configuration, we get to see that there is an interaction between interaction of the forces between the frame and the moving parts of the machine. Things will be much more complicated once the machine starts operating, and that's what we are going to show. So the important takeaway is that the frame is subjected to a force, and in this case it is exactly the weight of the machine. That makes sense because the frame is holding the weight of the machine, so the frame is subjected to this force and nothing else. But now since this force is not time varying, it is a static force, so the effect of this force is going to create some static deflection on the frame. It is going to create some static stress, static strain, static strain energy density, whatever. So if these stress, strain energy are within permissible values, then the frame will be able to bear the load of the machine. If it exceeds the critical value, then the frame will be undergoing failure and the frame will be damaged. So that is the theory of, that is what theories of failure and strength of material tells us. But as I said, things will be much more severe once the machine starts operating. Let us see how. So now we will come to dynamic forces in operating machines, right. So the previous case was that of a non-operating machine. It has not even started, so it is only having its weight, nothing else. Now let us say the forces have the machine has started, it is operating, and therefore this machine has started rotating. This has only a rotating member, nothing else. So there is this shaft which has started rotating. What we will find out is that due to its operation, dynamic or time varying forces are generated in the machine, which will now get communicated to the frame. So again, to repeat myself, in the case of non-operating or static machine, we find it's only the weight of the machine which will pass through to the frame. But here, due to its operation, we will see other forces which are not time varying, which are time varying, which are not static, but they are time varying, and they will pass on to the frame. So let's see how. And as usual, even in this case, we must have the total forces and the total moments to be 0. So just like we did the equilibrium condition, equilibrium configuration for a non-operating machine, similarly what we will do is that once the machine has started operating also, we will try and fix up what are the equilibrium condition in terms of forces and in terms of moments. So we will find the equilibrium condition. Remember, the forces will come through the mounting points of the machine. So again, if this is the machine that we are looking at, the mounting point is probably here as is visible from this diagram, and there will be one from the other side also. So even when this machine is rotating, it is through the mounting point that the forces will come on the machine, and similarly the forces will transmitted by the machine to the ground over here through the mounting point. Because the mounting point or the revolute joint in this case, or the bearing, the physically what is the bearing in this case, will be the interconnection between the rotating part and the static part of the machine. So the mounting forces and torques will be generated, and they will get as a reaction to the forces which are acting on the machine, the reactive forces to that will be transmitted to the frame. Now the issue here is, and to explain again myself schematically, so let's again consider this as a machine. Again, we are not very careful as to whether this is a turbo machine or something else. The details of the machine are irrelevant at this point. So all we understand is that this blue box contains some rotating You can even say some reciprocating parts also, but I will concentrate only on the rotating part right now. So let's say this contains a lot of rotating parts, and this is attached to the frame, which is shown by this black line. It is attached to the frame through these gray mounts, right. So again, if you take an FBD of both the machine as well as the frame, this is what you should see, that through the mounts there are some forces, there could be some torques also, which is shown by these curved arrows. So because of the forces which are getting transmitted to the machine from the frame, there will be an equal and opposite reaction pair which is coming from the machine to the frame. So our objective is to understand what are the forces and moments which are getting transmitted due to the operation of the machine from the machine element to the frame. So let us frame our first objective. We will make that a little formal also. So the first objective would be to understand or analyze the forces or moments transmitted to the frame due to the operation of the machine. This will be our broad objective, and how to determine this is the question that we will try and answer within the next few hours of the talk. So determining these, the magnitude and the direction of these arrows and these moments is what the talk is going to focus on. But then the question arises that what is the big deal in determining these forces and moments? Why do you think determining these would be important? Well, the for that we must understand what is the effect of dynamic forces transmitted to the frame. Just a couple of minutes ago I emphasized to you that if it is a static force which is getting transmitted to the frame, it is going to create a static stress, it is going to create a static strain, and you will have some theories of failure to predict whether the frame will be able to endure that kind of loading. But if it is dynamic forces which is acting on the frame, if the forces are so if the force is time varying, something like this, then you cannot expect a stress to be constant. Stress cannot have a plot something like this. This is not possible. So dynamic stresses or time varying forces will lead to time varying stress, strain and whatnot. Okay. So the problem in the analysis of dynamic stresses and dynamic strain is that obviously from your theories of failure and design of machine elements course, you would have come to know by now that if the material is subjected to fluctuating stresses, then the theories of failure says that the critical limit, which is the endurance limit in this case, is much lower. So therefore the material is more susceptible to failure in case there is a fluctuating stress that is created. So the frame will be more susceptible to failure if there are dynamic forces acting on the frame, because such dynamic forces would lead to fluctuating stresses on the frame, and as you know that these fluctuating stresses will lead to fatigue failure, and the critical value of these fluctuating stresses is now dictated by the endurance limit as opposed to the static case. In the static case, the static stress will be decided by the critical value of the yield stress of the material. For all class of materials, we know that the yield stress is greater than the endurance stress, and therefore materials will be more susceptible to failure if there are dynamic stresses acting on the material. So therefore, as far as the design of the frame member goes, it is very critical we understand both the static load which hits the frame as well as the dynamic load which hits the frame, and therefore we do a more complete analysis to make sure that the frame will sustain the loading during the operation of the machine. Worse still, the dynamic forces will, these fluctuating forces, any force which is fluctuating on a member will tend to vibrate this member, and once you have vibration set up in, typically again in an automotive situation, these vibrations will hamper the ride quality of the automotive vehicle. Similarly, if on the frame, you must understand, again looking from the automotive, once there is a vibration set up on the chassis, because there are other members like the, let's say the panel of the chassis, let's say the transmission, and all other members are getting bolted to the chassis itself. So if the chassis is set into vibration because the engine is causing these forces which cause this chassis to vibrate, then everything else will vibrate, and all of these put together will lead to a huge noise, and at the end of it you will have large compensation for the ride comfort. The ride comfort, as I said, will get compromised. So one is the issue of failure of the frame, and the other is the issue of ride comfort. So let us take this example to demonstrate to you how things will go bad if there are lots of dynamic forces getting transmitted to the frame. So as I said, we are going to talk about a typical automotive example. So at present we are concentrating only on the automotive engine. So engine, let's say, is the primary source of the vibration in an automotive car. So if the engine starts operating, then obviously there will be some rotating part, there will be some reciprocating motion within the engine parts, and as I said, because of the rotation and reciprocation of some parts, there is, through the engine mounts, there will be a large force which will get transmitted through the frame and the chassis. But then you see the BIW, the panel which makes the car, is also getting mounted on the chassis, right? So once there are fluctuating forces on the frame starts vibrating, and once the frame starts vibrating, these vibrations are communicated onto the BIW or the panels of the car. And since I am going to sit on a chair which is again mounted on this panel, if this mount starts vibrating, I will also start vibrating as a passenger. This is definitely going to be annoying for me, and therefore steps must be taken to control this. And also now you see, despite the vibration of the primary source, that is the engine, being concentrated in a small region, and the engine is actually within a compartment wherein the passenger possibly does not bother to know what is happening in that compartment. But the problem is that this small engine which is residing in this big car is actually able to cause a global annoyance onto the entire BIW, right? So a local problem has become a global problem now, because everything was getting connected to the frame, right? So it's very important that you don't transmit a large amount of these dynamic forces onto the frame and set up the frame to vibrate, because if the frame vibrates, then this entire panel will vibrate, and no matter where the passenger is seated, he will have some discomfort, he or she will have some discomfort. So that is the purpose in trying to analyze the dynamic forces. So this is exactly what I told you, just I will run through my slides, none the same. So engine has moving parts which produce the dynamic forces on the frame. The frame vibrates under the action of dynamic forces. The BIW, which is connected, by BIW I mean the body in white, and these are nothing but the panel members. So these panels are connected to the frame. Because the frame now vibrates, the BIW also vibrates, and you know that anything which causes vibration also makes sound, therefore there is lot of sound also which is getting generated. So this in any automotive company is a major concern, and this field is called vehicle NVH. NVH stands for noise, vibration and harshness. It is an industrial term, but anyway, at this point our purpose is not to study NVH, rather it is to study the dynamic forces which are created because of the machine, and to establish how much force is actually getting transmitted to the frame. As engineers, our purpose will be to make sure that minimal forces are getting transmitted to the frame, because if the forces are beyond certain limit, firstly it can cause the frame to fail because it cannot sustain fatigue load as much as it can sustain a static load, and also in automotive example, as I have demonstrated, it can cause severe issue in terms of ride comfort, which is basically dealt with in the subject of vehicle NVH. So with that, let us take our final objectives for this upcoming session. We will try and estimate the forces and moments which are transmitted to the frame in the machine which has rotating and or reciprocating parts. We need an estimate of the forces. If we know that the frame has to bear an IC engine which is rotating at such and such speed with such and such gas pressure and so on and so forth, we should by the end of the session be able to estimate what is the forces and moments which are hitting the member. If we know what are the forces and moments which are hitting the frame, then possibly you can take some corrective action and you will be able to predict that this is the vibration level of the frame. Better still, if we know how the forces and moments are transmitted, we should come up with better design which minimizes the transmission of forces and moments to the frame. So these forces and moments which are getting transmitted are called, in other words, shaking forces and shaking moments. So these forces need to be minimized. So we will try to give you better designs. We will try to present some simplistic designs wherein these forces will get generated, but then as an improvement towards it, we will talk about better designs which will try to neutralize these unbalanced forces and minimize these unbalanced forces such that the frame is supposedly clear of these dynamic forces. And this is what we mean by balancing. By the forces which are getting transmitted to the frame are called unbalanced forces. I think I should make this remark. So forces transmitted or moments transmitted to the frame are called unbalanced or shaking forces and moments. And by balancing, what we mean is the following. By balancing, our objective would be to nullify the unbalanced forces or moments. We will try to kill these unbalanced forces because we know they are detrimental in terms of the performance of the machine. So in the context of dynamics of machine, balancing means you should try and prevent the transmission of the forces from the machine which is operating to the frame, because this is harmful in terms of the reliability of the machine. It is harmful in terms of, let's say it's a grinding machine, and if you have large amount of forces which are getting transmitted onto the frame of the machine because of the grinding wheel which is operating, then what will happen is that the job will start vibrating, and if the job starts vibrating, you will not be able to get a good quality of finish. So whenever there is a large amount of shaking forces which are getting transmitted to the frame of your machine, there is something detrimental about the quality and performance of the machine, other than the fact that the machine will reduce in terms of its life. So therefore it is very pertinent that we understand how much is this force getting transmitted, and also it is very important to try and contain these unbalanced forces, which is what we are going to do in the perspective of rotating and reciprocating machines. So as a prerequisite, before I step in further, I would please like you to refresh the concepts in engineering mechanics, especially the equilibrium conditions, I would expect that you will be good in drawing free body diagrams, which is a very important tool, and in my experience I have found most engineers are lacking in this proficiency. So I will give you a good piece of advice that please concentrate on engineering mechanics, because that's supposed to be a foundational level subject. Also you need to have some visualization aspects clear in your mind. So to aid you with your visualization, we have some animations. These have been also posted in your course pack. So some amount of imagination and visualization will be useful none the same, but there is absolutely no compromise with this prerequisite of engineering mechanics, which hopefully you have studied in your first year of engineering. The application focus in my talk is going to be turbo machinery and internal combustion engines. So turbo machinery mainly from the context of rotating parts, and for internal combustion engines we will see an example wherein a machine has both rotating as well as reciprocating parts. So as I said, the objective will be to minimize the transmission of forces. We will see that objective can be well ascertained in the cases of turbo machinery, but sometimes in the cases of internal combustion engines, when you have reciprocating parts, this objective is very difficult to actually satisfy completely. This is what we will look. Any questions at this stage? DGI, please let us know what's your question.
Good morning, sir.
Good morning.
Sir.
Good morning.
NVH is stand for noise vibrated, and H is
NVH stands for noise, vibration, and harsh.
Hertz.
H stands for harshness.
Okay. Thank you, sir. VIW, sir.
Body in white. So the panels of your automotive panels of the automotive panels which make up the car, they are called BIW. They are made of thin sheets. They are called BIW in industrial terminology.
Thank you, sir.
Okay. Any other questions? Yes, GHRC, please go ahead with your question. Yeah.
Good morning, sir. Sir, I have one question.
Yeah. Carry on.
So, can you please give me some examples of vibration caused due to machines? Like any example?
Yeah, one is the example of a car. If you have a car with an engine, with a transmission, and so on and so forth, because the engine is operating, there are large amount of forces which are getting conveyed onto the chassis on which the engine is mounted, right? And then the passenger seat is also getting mounted on the chassis. So therefore, if you are the driver, then you will feel the vibration. The chassis is vibrating. Are you clear on that?
Right. Okay, sir. Thank you.
Similarly, if you take a lathe machine, if you take a grinding machine, everything which is operating, because of its operation, will create forces which will tend to vibrate the job or the tool piece. If in a lathe it's a tool piece, in a grinding machine it is the job, and if the job starts vibrating as you are grinding, then you will obviously get a bad surface quality.
So, and other than balancing, what can reduce the vibration?
Oh, there are many things. There are many things which can reduce vibration. We can talk about that on our other course, but this is about balancing. Balancing is one way in which you can reduce vibration. There are many other ways in which you can reduce vibration. We can talk later on that.
All right. Thank you very much, sir.
PCE, please ask your question.
The machine is uniform and the mass distribution is also uniform. Then how a rotating machine can produce a varying forces in the machine?
SSETN, please ask your question. SSETN, you are dumping the horse before the cart. We are not talking about aeroplanes or helicopters at this point. We will talk about them. Maybe I'll take your questions by the end of the course. Okay, so you're talking about aeroplanes, helicopters, domestic generators, and whatnot. Please try to understand with one example what is happening, and then we will definitely talk about all other examples. Don't at present think about too many examples and perplex your mind. Let's take 2 examples and carry on with our discussion. Definitely, if you still don't understand what is happening in an aeroplane or a helicopter or a domestic generator, we can talk about it before we end the course on the third day. DJI, you have another question?
Hello.
Yeah, tell me.
Good morning, sir.
Yeah, please be
Hello.
seated. Please be seated.
Sir, I have one question. Okay, thank you, sir. Sir, we are from Dwachar. We have one question. As you have mentioned, its balancing is nullify the unbalanced forces. But
Right.
in locomotive, we also read that is partial balancing. Partial balancing.
Yes.
So,
Yes.
is it correct to nullify or something is reducing
The objective will
unbalance?
be to
What should
nullify.
be the
What I
proper
said was
definition
the
of balancing?
objective would be to nullify the forces. But yes, in cases of reciprocating
Okay.
machines, it may not be possible to attain that objective. You will only be able to partially balance it. So that's the answer.
Okay.
The objective is always to nullify, but you may not attain the
Okay,
objective.
sir.
That's the problem.
Okay, sir. Thank you, sir. Thank you, sir.
Okay, let's go ahead with the lecture material now. So now we'll take a deeper dive into rotating machineries, and here we go. So you would have observed in typical garages they are going to do wheel balancing. This is again wheel balancing in probably some western countries taken from Google images. So let us understand what's happening for in the case of wheel balancing. So wheel balancing constitutes an example of what we call a single plane unbalance. So this time you have just a thin circular disc which is rotating, right? You have a thin circular disc which is supposed to rotate. Now in wheels typically what happens is that there is a non-uniform wear which is happening on the surface of the wheel. Because of the non-uniform wear, though in at the time of manufacturing the geometric center of the wheel was exactly equal to the center of mass, but once the wheel is undergoing some non-uniform wear, the geometric center and the center of mass no longer coincide, right. So let me draw it in my tablet to explain myself better. So at the time of manufacturing you have this perfect wheel, though my drawing does not show that it is perfectly circular, but let us assume that it is perfectly circular. So at the time of manufacturing everything is very idealized at the time of manufacturing. So you have the geometric center of the wheel is equal to the center of mass of the wheel. No issues on that. But then as there is non-uniform wear in the wheel, or the entire periphery, the entire circumference of the wheel does not wear in an identical fashion. Why is that? Because when you are riding through a road condition which is quite random, certain part of the wheel will be subjected to more rough wind, road conditions than some other part, right, which is obvious. So therefore the wheel will not wear uniformly, and therefore after some time the wheel will have exaggerated fashion. It could look something, it will not be flat though, so it will have, let's say, some profile of this kind, right. So now your center of mass is definitely not remaining the same, it's the new center of mass, whereas the wheel is rotating about a center, the axle of the wheel is somewhere here. So earlier you had the axle of the wheel and the center of mass to be exactly coinciding, whereas now the axle of the wheel and the center of mass is at a distance, it could be very small in microns, but it is at a non-zero distance because of uniform wear rate. Okay, non-uniform wear in this, even if you assume that the wheel is thin enough like your bicycle wheel or typically a motorbike wheel, but even then because of non-uniform wear rate you don't expect the center of mass of the wheel to be coincident with the geometric center or the point about which the wheel is moving. So as there is uniform wear of the wheel, the center of mass during operation will not be equal to the point about which the wheel is rotating. Okay, and we will see that this is what causes unbalance in a rotating mass in a short while from now. So this is one example. As another example, I would like to think about cams. So consider a cam, and cam by its very nature is not very symmetric object. So this is a cam, and you will see all kinds of cams again in IC engines where they are used to control valves. So this is a cam for you. So this is the cam mounted on the shaft. There is no reason to expect that the cam center of mass of the cam will lie on the axis of the rotating shaft. So the center of mass could be here. So cam is eccentric, which implies center of mass of the cam is not equal to the point about which cam rotates. So if I have to draw a front view of this situation, so this is the cam. So the cam is rotating about this point, whereas the center of mass is here. Okay, so this is the center of mass and this is the cam, and this eccentricity also could be pretty high, of the order of millimeters, maybe centimeters also. So unlike the case of wheel, the case of cam is definitely going to lead to eccentricity. So by eccentricity what we mean is the distance between these 2 points. So eccentricity means distance between center of mass and point of rotation. Okay. So obviously if you don't have an asymmetric mass like a cam, if you have a very perfect circular disc, then you should not expect this sort of a situation. But again, due to manufacturing variability, due to operational conditions, as the machine is operating, you will get to see, as it happens in the case of wheel, because of non-uniform wear, we are getting to see that after the wheel has traversed a certain distance, you will definitely see that the geometric center and the center of mass of the wheel is not coincidence. This can also happen due to manufacturing variability. You don't expect that all wheels will be manufactured with exact precision. Maybe in the case of wheels the manufacturing does take care. In case of other rotating objects like your machine parts in lathe or other manufacturing tools, there will be some manufacturing variability which will result in an eccentricity. What we mean by eccentricity is that the geometric center about which the wheel is supposed to rotate or the disc is supposed to rotate, even if it is circular, is not matching with the center of mass. There could be a micron level difference, as let us say in the case of grinding wheel. Grinding wheel is also another example. Again, because of the distribution of the abrasive particles which are mounted in the grinding wheel, and these abrasive the grinding wheel itself undergoes a non-uniform wear rate. Because of that, you would not expect that the geometric center will coincide with the center of mass of the grinding wheel during its entire course of operation. So again, from time to time you have to balance this grinding wheel, because if you don't do that, it will lead to a problem, as I will explain in my next slide. So we have talked about at least two good examples of wheel balancing and radial cam where we have a single plane unbalance, because we are talking about one object which is a very thin object and therefore it's a planar object. This is undergoing rotational motion, but this rotational motion, as we will now see, is going to lead to unbalanced forces. Let us see how. So again, here is the schematic drawing of it. So here you have this blue rotor which is mounted on a shaft, and this shaft is put on a bearing, and the center of mass, which is a red dot over here, is not coinciding with the geometric center. The geometric center is the point about which the rotation is taking place. So now what is happening, as this mass rotates, there is a center, other than the fact that there is a weight, but weight is just a static force, so we are not going to worry about this weight aspect anymore. We are going to worry only about the dynamic forces. So let us see what happens once this rotor is started rotating. Once this rotating shaft has started rotating, because of this eccentric mass, a centrifugal force will be created, right? So this centrifugal force is indicated. This is the isometric drawing. So the centrifugal force is indicated by a red arrow here, but now this rotor is subjected to a centrifugal force, and to balance this rotor shaft system, the bearing must put in these forces. So the arrows indicated by green on the left and right end of the shaft indicate the force which the bearing puts into the rotor shaft system, such that the rotor shaft system can remain in equilibrium. So these two forces supposedly balance the centrifugal force, right? But then always whenever there is an action, there will be a reaction, which means if the bearing has put in these green forces to the rotor shaft system, the rotor shaft system will in turn react back and put in equal and opposite forces on the frame, right? So therefore the frame will be subjected to equal and opposite forces to these green forces, and therefore these forces will be the unbalanced force in this case. So centrifugal force, as I said, is given by the good old formula, mass times eccentricity times omega square. You will recall the centrifugal force is given by, in your engineering mechanics class you would have got it as mr omega square. R this time is, we are changing the symbol of R, instead of R we are calling it E. So E is the distance between the center of mass and the geometric center. So the centrifugal force, because of this mass which is lumped at the red point, is going to be me omega square. Remember, as this object is rotating, the red dot over here will keep rotating, and therefore it will cause a centrifugal force of me omega square. And the trouble here is, you may say that what is the big deal if there is some micron level eccentricity that is created because of non-uniform wear pattern. The trouble is this, that even if E is small, of the order of microns, omega can be very large, and that is typically the problem in turbo machineries. In turbo machinery we are talking about really high speed machines which operates at 10,000 rpm or even higher than that. So in that cases, even a micron level eccentricity is going to cause a large unbalanced force, and therefore we see that the total unbalanced force is depending quadratically on the rotational speed, whereas it is depending only linearly in terms of the eccentricity. So therefore a small eccentricity can cause a large unbalanced force if the speed is high, and therefore we have to care of even micron level unbalances which are created due to manufacturing precision or whatever. So therefore at present what we have found out is that because of the rotation of this rotor shaft system, there is a centrifugal force, and this centrifugal force at each instant has to be balanced by this green forces, which are the bearing reactions. But then you will observe that the centrifugal force itself, though the magnitude of it is constant, which is me omega square, the direction of it is always changing, because as the orientation of the center of mass is here, the centrifugal force is directed in this direction. At a later instant, the centrifugal force could be in some other direction because the orientation of the mass is somewhere else. I will do another drawing in my tablet to explain myself better. So So let us consider at some instant you have a nice circular disc but having some eccentricity, so the center of mass is here. So at this instant you will get a force which is m, this force m e omega square is, this force m e omega square is directed from the point of rotation towards the center of mass. But since this object is rotating, because this object is rotating at a speed omega, at a later instant, this, I should draw better circles than this, at a later instant the center of mass would have come here because the disk itself is rotating together with the center of mass. So at a later instant, so this is t equals to 0 and this is t equals to delta. The center of mass itself has rotated. So at this instant now, again the centrifugal force in terms of magnitude is given by me omega square, but between these two drawings you will realize that the direction of the centrifugal force has changed. And that's what, when we, that's why we will say that it is, the centrifugal force is a rotating force and therefore it is a dynamic force. I will explain myself better through an animation which is upcoming for you. So here we are. So here is the, so in the last slide we saw that there are some green forces. These green forces are given by the bearing to the rotor shaft system, and therefore the frame in turn will get equal and opposite force to these green forces. This is what is indicated here. Now this entire system is undergoing rotation. So the angular orientation of these red arrows and green arrows is always going to change from instant to instant, and therefore the reaction force to this green arrow is also going to change its orientation. At a certain instant it is showing this. So between different orientation we see that the frame is subjected to a constant magnitude force, which is the unbalanced force, which is given by me omega square. But then if you look at the component of this force in some particular fixed directions x and y, then you will get to see that it is the cos and the sine component of me omega square. So f e the component of this force f is me omega square. The component of this force along the x direction will be cos of omega t plus phi. So this is the angle cos of omega t plus phi, and similarly along the sine direction it will be sine of omega t plus phi. So phi could be an arbitrary phase, but the important point to realize is the following, that though the force is constant in magnitude, it is constantly changing, it is constantly rotating, which means the force along a fixed direction will always change in direction in its magnitude. So if you can see my animation now, what I have here is the actual eccentric force. This center of mass, this disc is rotating counterclockwise, and as it is rotating counterclockwise, the center of mass is always moving in this fashion. So following the motion of the center of mass, the green arrow here, which is the centrifugal force, it remains constant in magnitude, but it constantly changes its orientation. The orientation of this green arrow is always from the point of rotation to the center of mass, and the blue arrow in turn is the projection of this force along the x direction. Similarly, you could have a projection along y direction also, but at this point let us concentrate about what is the force acting in the x direction. So the force acting on the x direction is always going to be the projection of this green arrow along the horizontal. So in this animation what you see is, as this center of mass is rotating at constant speed, the projection of this centrifugal force, this constant magnitude centrifugal force, keeps changing, and when you do the mathematics it comes out to be a cosine component in this case, where omega t is measured from the horizontal, and therefore you will, and if you have to plot it out, if you plot the magnitude of this force with time, this is the kind of plot that you are going to get. Okay. So as the centrifugal force is rotating, it is constant in magnitude, but the projection along x is going to rotate in a cosine fashion. The y component would have shown up a sine fashion. So now if I look at what is the force along the fixed direction, which is x, what is the force along the horizontal direction which is being subjected to on my frame, then we will get to see that the force is not constant, but rather it is varying. It is varying in a cosine fashion, as you see in this graph. So that should make it clear to you, as some of you were asking me, that in a rotating system how is that you are getting a dynamic force. This is exactly how. If it is perfectly balanced, that is if the geometric center and the center of mass is perfectly coinciding, then there is no way you can get this centrifugal force. There is no question and asked, and therefore the system is completely balanced. But due to operational issues, this centrifugal force will kick in, and despite the centrifugal force having constant magnitude, the component of the centrifugal force in a particular direction will keep fluctuating, and that is what we see here, and that is exactly what we refer to as the unbalanced force. So carrying ahead, what we see, this type of forces where we have sinusoidal or cosine kind of variation, we refer to them as harmonic forces. Harmonic because it has a single frequency, right? When you do a more advanced course in vibration, you will be more accustomed with this terminology, but at this case, in this course, it is sufficient for you to just understand that if you have a time varying force and the time variation is in the form of sine or cosine, only sine and cosine is what we will take. Please do not consider tan, sec and cosec and other combinations. If the time variation of the force is either sinusoidal or cosinusoidal, then, or of this form, I think I will write that, a quantity, a harmonic quantity is of the form x of t equals to a cosine omega t plus phi, which is also b cosine or maybe sine omega t plus phi. Okay. This is what we will call as harmonic quantity. It is designated by an amplitude and a phase and a frequency. So these are the important quantities. At present, we don't need anything more about harmonic quantities other than this definition. So we will get going with this. So therefore, let's consolidate what we have learned. At present, we are able to figure out that unbalanced force due to rotation is nothing but the centrifugal force, the magnitude of which is me omega square, and if you want a balanced condition, then what we are looking for is me equals to 0. If either the object does not have mass, which is ridiculous, all objects do have mass, or better still, if the eccentricity of your rotating element is 0, which means the center of mass of the rotating element can be made to coincide exactly on the axis of rotation, then you will have this E factor or the eccentricity factor to be 0, and therefore there will be no centrifugal forces generated, and therefore you will not have any unbalanced force whatsoever. So unbalanced force, we realize, is proportional to m times c. It is proportional to the mass, it is proportional to eccentricity. So again, what that means, that if you have a large mass but at small eccentricity, it can create havoc. If you have a small mass at a small eccentricity, that does not create such an amount of trouble, but if you have, again in turbomachinery, we have large masses, so even a small amount of eccentricity in these large masses can lead to large centrifugal and hence unbalanced force. So, but the good thing is that if me is 0, then the machine is balanced for all omega. So if you can check that mass times eccentricity, which essentially means eccentricity is 0, if eccentricity is 0, then no matter what be the speed, at all conditions centrifugal force is 0, and therefore at all speeds it will be balanced. So that is the near ideal condition which we would try and achieve. So me, the mass times eccentricity is what we will refer to as the unbalance of the rotating machine. So it is the mass of the machine itself is not very important. What is very important is mass times eccentricity of the machine. So mass times eccentricity is termed as the unbalance in the context of rotating machines. So let us see now we have single plane unbalance. So let us now try and detect, typically if you have visited a garage and seen how they are doing wheel balancing, this is how they will do it. So wheel balancing in the case of non-uniform wear can be detected very easily. So let us take this blue object to be our wheel, and it is mounted on an axle, and it is asked to be it is rotated about these bearings. Now let us put on this wheel some markers, one cross, one plus, and one circle. So the cross is in red, the plus is in green, and the circle is in black. So these markers are some random markers which are oriented in some random fashion. If the mass is actually statically balanced, which means the center of mass is exactly the geometric center, then every time you repeat this experiment, you rotate the mass and you let the mass take a static equilibrium configuration. Every time the mass is in the static equilibrium configuration, you will be able to get a random position of your marker. You will not get the same position of your marker. Every time you spin this disc, it will settle at some random position. Whereas if there is an eccentricity, if there is a center of mass, then which is not aligned, which is not passing through the center of rotation, in that case there is only one configuration that is possible in the static condition of the shaft, which is this. You cannot have a condition where the center of mass here and the body is in equilibrium, because in that case the moments will not balance, right. So if the moments have to balance, the only possible condition of static equilibrium when you have the case that the center of mass is not coinciding with the center of rotation is the case where the center of mass is directly below the axis of rotation. There is one more configuration which is above, but that is an unstable configuration. So you would not get it. The stable configuration is where you will have the center of mass directly below the axis of rotation. So under static condition, the unbalanced rotating disc occupies a fixed configuration, and the fixed configuration itself is the one in which the center of mass lies directly below the axis of the point of rotation, if you may call it. Whereas if it is balanced, then any of these configurations is possible, because the center of mass is at the geometric center. So there is absolutely no moment that is created by the center of mass through the axis of rotation, and therefore you will have all these conditions to be completely same. So therefore if you had put markers at some arbitrary orientation, any of these orientation in terms of the markers orientation is an equilibrium configuration. So what they will typically do in a garage is that they will put some markers at some random location and keep changing the orientation of the wheel. If they keep saying that the equilibrium configuration is where the markers are could be in any haphazard location, then they are certain that the wheel is balanced. Whereas if they keep saying that there is only one possible equilibrium configuration through their repeated experimentation, then they will conclude that the wheel is not balanced, and they will take the necessary action to balance it, which is what we will also do. So the idea is very simple. So now that the single plane unbalance has been detected, the question is how do you mitigate it? So we are talking about a disc now, and we have found out that to our dismay that the center of mass, which is indicated by this red blob, is not coinciding with the geometric center, rather it is shifted away from the geometric center by a certain amount, which we denoted by E. So the best thing to do is to put another mass at another eccentricity. Whenever you have a problem, try to create a counter problem in the exactly the opposite direction, and these two, the problem and the counter problem, it is like the antibiotic effect. When you have a germ sitting inside you, you try to bring in another germ which will actually fight this germ. So that's what we tend to do in this case also. You had a eccentricity here, you try to put the opposite eccentricity on the exactly the other side such that m times e is equals to m prime times e prime. Now what happens when this object rotates? There is a centrifugal force me times omega square, there is an equal and opposite centrifugal force m prime e prime omega square. So as a result, the total centrifugal force that is acting on the body is actually 0, and therefore there is no centrifugal force in totality, and therefore there is nothing which is getting transmitted through the bearings to the frame, and therefore we would have achieved our objective, which is to kill this unbalance. So in this case, if we do an m prime e prime, then there are no unbalanced forces, bearing reaction, stress, etc., all are cancelled, and we have the happy situation that we have balanced this rotating object. So this rotating object, again to give you a concrete example, could be a wheel, and you tend to put a mass on the opposite side of where the eccentricity lies, and that will solve the problem for the time being. Another naive idea is that, or maybe sometimes even this happens in very practical situations, is that this disc may not be accessible to us. It may be closed, there may be a casing, and you may not be able to put the counterbalance. This m prime e prime is called the counterbalance. The counterbalance may not be possible to be put exactly in the location that you are desiring. So in that case, what do you do? So at times it is not possible to add mass directly opposite to the eccentric. It is just a practical problem that it is not accessible to you and you are not allowed to put the mass. So therefore, a naive idea could be that, well, if it is not accessible, put another mass again with the same idea, but maybe at a slightly offset distance. So here you had the shaft, and the shaft was mounting a rotor which was eccentric, and the rotor to eccentric is what is shown in red here. So as I said that it was not possible this time to put a counterbalance, the green one, exactly on the rotor because the rotor was not accessible to you. So what you thought was that let's put another counterbalance using the same idea, m prime e prime, at some distance away. Wherever you find the nearest distance of accessibility, you want to put another counter mass at this point, and then let us see what happens. So again, if you take the left side view, if you view from the left side, what happens? You get to see two centrifugal forces, one the red and the other the green, right? So the centrifugal forces, since you have obeyed the rule me is equals to m prime e prime, the total centrifugal force even in this case is perfectly balanced. So therefore, the forces on the shaft is perfectly balanced. There is no reason to think that the shaft is not balanced in terms of the forces. But there is a problem. The problem is that these two equal and opposite forces this time, which is due to the red one and due to the green one, is now going to create a moment. And to balance this moment, there has to be a bearing reactions which has to come in. So each of these two eccentrics are going to put in forces of the value me omega square, and because they are separated by a distance of a, the moment which will be created by these two forces would be me times omega square times a. But so the forces by themselves have actually been balanced. There is perfect equilibrium in terms of the forces, but unfortunately the moments have come in, and because the moments have come in, the bearing reactions will not be 0, but bearing reactions will be such that they counter this moment. So what you want is R times L should be equals to M. M is this moment. So therefore, though you have balanced the forces, you have not balanced the moments, and because you have not balanced the moments, the bearings are putting in equal and opposite forces to create another moment such that in terms of the moment balance also, the shaft is satisfying its equilibrium condition. Now once the bearing is putting in some force to the shaft, it will get back the reaction forces which will go to the frame, and therefore again the frame will receive this time two equal and opposite forces, one coming from the left side and the other coming from the right side. The forces are equal and opposite, but again these forces are going to create a moment on the frame, and as a result the frame will be subjected to vibration and also stress. So therefore this does not solve the problem. So what we need is, remember, when we are talking about balancing, it's not just about the forces, it is also about the moments. It may feel to you that it is only the centrifugal force which is causing unbalance. True, it is only the centrifugal force, but to balance the system in totality, we need to balance both the forces as well as the moments. If we leave the moments unbalanced, then again the bearing reactions will be induced, and these bearing reactions will be sufficient to induce dynamic fluctuations in response as well as stresses onto our frame, and will cause problems as I narrated few minutes back. Okay, so this is what is called an external balancing. So in external balancing, what we do is that now that we realize it is not a good idea of putting just one counter mass, what we will try and attain in this course is that what we will try to think is that instead of putting one mass, let us put two masses, which is called two plane balancing, and that is where we are trying to go. So in two plane balancing, in addition to the actual eccentric, which is denoted by red, we will try to put two unbalanced masses in two counter masses at two different planes, which will be separated by a distance a and b. So the fact that we will have a second unbalance to put will actually ensure that both the forces as well as the moments are kept to 0. So what we have seen here, that if we add the counter mass only in one plane, then it is not possible to satisfy the moment equilibrium condition, and as a result the bearing reactions will be induced to satisfy this moment equilibrium conditions. So to mitigate this idea, we are now proposing a two plane balancing method, wherein we try to put the counter masses not just in a single plane but possibly in two different planes, and when we put in two different planes, as we will show, then it is possible to both satisfy the force equilibrium as well as the moment equilibrium. And when both these conditions are satisfied, happily the bearing reactions will have no reason to get induced. So bearing reactions are completely nullified in this case, wherein both the forces as well as the moments are taken to be 0. So the force and moment balance in this case will mean what is the centrifugal force in this case? We are now talking about one and unbalance, which is this indicated by the red one, and this is countered by putting two counterbalances in exactly opposite direction. So therefore the centrifugal force which is created by the original red unbalance is m times E times omega square. The centrifugal forces which are created by the new counterbalances which are incorporated in the member are the green and the blue ones. They induce centrifugal force m1 E1 omega square and m2 E2 omega square. But as you know, nothing since omega square is a common factor on both sides of the equation, we can cut it from both, chop it off from both the sides, and therefore the condition of force balance is me equals to m1 E1 plus m2 E2, right, because omega square factor is common across the equation. Similarly, when you take moment about this plane, which is about that red plane, so then there is no moment which is created by the original eccentric, the red one. The moment which is created by the green one is m1 E1 omega square times a. The moment which is created by the blue one is m2 E2 omega square times b. Omega square cancels from both sides and you are left with this condition. So m1 E1 a is equals to m2 E2 b is a condition which will enforce that both the moments as well as the forces, these two conditions, when you enforce, you can find out what should be m1 E1 and what should be m2 E2. So these two equations will enable you to actually find what is m1 E1, what is m2 E2. In other words, if m1 and m2 is fixed, you can find out what is E1 and E2 from these two conditions, right? And therefore if you have a and b fixed, so that is, and then you should be able to solve this equation and find out what are the required eccentricities. So the happy thing about this formulation is that it balances both the forces as well as moments, and since both forces and moments are balanced, there is no bearing reaction pair which is induced, and therefore the situation is completely balanced. But even then there is one issue, that is this portion of the shaft will actually see some stresses. That is very easy to actually see, because if you consider, if you take a section here, then this section of the shaft is going to see only one centrifugal force, and therefore this portion of the shaft will have to induce a bending moment, and therefore it will be stressed up. So the portion between the two counter masses will be stressed, the shaft will be stressed, but happily there is nothing which is getting transmitted to the frame. The frame is saved from any dynamic forces. It is balanced, but the shaft itself as a rotating member will be stressed. So you will need a good shaft material which can actually bear that stress. So that is unavoidable. So this is just the price that we have to pay. In case of internal balancing, when you were able to balance it with one mass which is put directly opposite, in that case even the shaft was not stressed, because there is absolutely no centrifugal force, no moment, nothing. The shaft is saved from any stress. So that is internal balancing. Obviously it is more favorable because the shaft is also saved, but in this case this red region of the shaft cannot be saved, because when you take the section here you get to see that in this portion of the shaft there is a force, and to balance this force there has to be a bending moment created in the shaft, which in turn will create the bending stresses and subject the shaft to these stresses. So that part, as I said, is unavoidable, and but this is a good solution in practice, and this solution is referred to as external balancing. Okay, before moving on to multiplane balancing, because this is multiplane balancing is a little more demanding in terms of visualization. Let me pause for a while to see if there are any questions and clarifications sought from the single plane unbalance that we have talked about in this part of the talk. We'll have a 5 minutes question answer session. Yeah, someone just asked how in case of rotating discs you had unbalance generated. I hope he is clarified. If you are not clarified, please feel free to ask me the question now. How will we estimate the unbalanced force magnitude? The unbalanced force magnitude is m times E times omega square. So the mass of the rotating system multiplied by the eccentricity. Eccentricity means the distance between the center of mass and the point of rotation of the rotating disc. So mass times E times omega square is the magnitude of the unbalanced force. I think it was written in one of my slides also.
You have tell about the detection of single plane unbalancing. We find that the unbalanced mass is just below the point of rotation. But how
Yes.
can we find the distance?
No, we cannot find the distance direct. We are just detecting. See, detection does not mean that you are actually finding the magnitude of unbalance. You are just detecting that there is a single plane unbalance problem, static unbalance problem associated with this machine. That's all. Actually, how to estimate the unbalance, there are separate experimental procedures for it, but the title of the slide was about detecting. Firstly, you have to understand whether yes or no, whether there is an unbalance or no, there is no unbalance. Okay. So when I said it is detecting the unbalance, it is only about knowing whether m times E is equal to 0 or is not equal to 0. If it is not equals to 0, there are separate experimental procedures by which you have to actually determine how this m times E has to be estimated in your problem, but that was not talked about in this lecture.
Well, thank you, sir.
Good morning, sir.
Good morning.
So we were discussing on first order of harmonic disturbances. Why didn't we consider second order, third order of omega?
In rotatory unbalances, you will not get second order and third order. You will only get first order. You will get second order in case of reciprocating machines. You will not get it in rotating machines.
Thank you, sir.
At least for eccentric unbalance, at present we are doing eccentric unbalance. We are not in eccentric unbalance. We are not going to get any higher orders. We are only going to get only first order.
Thank you, sir.
Okay. PHGCT is asking me how is controlled addition of mass at a particular location is done. So again, depending upon the sophistication of the garage, this could be just an iterative hit and trial kind of procedure. They keep adding mass till they see that the unbalanced forces, which is actually sort of felt in the bearing. So if the bearing is put on some kind of spring suspension, you will be able to see that through the deflection of those springs, that whether how much is the force that is getting transmitted to the bearing. So you keep as a hit and trial, again depending upon the sophistication of the arrangement. The most crude arrangement would be just keep putting it in various points till you observe minimum deflection in your springs or minimum vibration on your bearings through the springs. So when you observe that, you feel that your machine is totally balanced. But yes, there are more advanced experimental techniques to determine the unbalance and to estimate it also. You can read through the literature of experimental estimation of unbalance. If you want, I can post some also in your course pack, but definitely that's not a matter of discussion in this lecture. Yep. Next one, how to locate positions of unbalance. As for CEC, I think we have just answered your question. The position of unbalance is detected in an experimental setting using some instrumentation which I cannot talk. Here we have talked about how to detect. It is not about how to locate that position. If you want, that can be done with some experimental techniques. There are balancing machines available for this purpose. The principles, how the balancing machines work and what sort of measurements have to be done, it will take us too far out of the scope, but if you want, I will definitely post some literature on this for your supplementary reading. How wheel balancing in a car is done? As I said, depending upon the sophistication of the garage, whether it is our roadside garage or it is some sophisticated western garage, this can be done at any level of sophistication. The most crudest arrangement is what I have described. There are more advanced techniques also wherein they employ accelerometers and force transducers to actually estimate the exact unbalance and determine its location. So all that is possible, but these are experimental techniques and it is not within the curriculum of a BTech program. But none the same, if you are curious to know it, I will post one material from Bruel and Care. Bruel and Care is one renowned organization making equipments for testing vibration. So one of those materials will discuss in details as to how this experimental investigation is actually done. Okay, so that's okay. SGGCT is asking how to decide when to use external or internal balancing with application. Internal balancing is always feasible if you can do it, but if the problem with internal balancing sometimes is that it is not accessible. For example, again if it is a turbine casing, if it is an operating turbine, then no one will open the turbine casing and allow you to put the masses wherever you want to. You can only put the masses only on the casing and nowhere else. So in such cases internal balancing is ruled out, you have to only settle for external balancing simply because of accessibility issue, which is a very practical problem none the same. So therefore theory will say go for internal balancing whenever you have a choice, if it is possible. If it is not possible, then you have to settle for external balance. Okay, fine. We'll go ahead now with multiplane balancing problem. So here again, this is coming back to my slides. This is a typical turbo machinery. You get to see a row of these multiple of rows of turbine blades being mounted on the rotor shaft. Now till now we were talking about one rotating disc which was thin, but by no stretch of imagination this rotor can be assumed to be thin. Now what can happen is that at each row of these turbine blades you can have different eccentricities, because these turbine blades get manufactured at some different location and they get assembled row wise or whatnot. You could have a situation that each row of these turbine blades brings with it a certain amount of unbalance. So when talking about a wheel, it was a single wheel, but now when we are talking about rows of turbine blades, each row is like a disc. Each row of turbine blade can be construed to be like a disc, and each of these rotating discs could have its own eccentricity. Fortunately, we will think that none of these have manufacturing variabilities and therefore everything is ideal. But in practice, again what will happen is, because of manufacturing variabilities, you will not expect each of these rows to be perfectly balanced. Each of these rows will be inducing some eccentricity. Again, that eccentricity could be really small in terms of microns, but then you must understand that the turbo machinery applications demands a very high speed of these turbines, typically 10,000 rpm, of the orders of 10,000 rpm. So you can imagine that such high speeds, even a small eccentricity value, and the mass also this time is pretty large. So therefore, even a small eccentricity in each of these turbine rows could cause a large centrifugal force, which could be detrimental and could lead to failure of these turbo machinery applications. So as I said, we are going to talk with the specific application in mind, that of turbo machinery. So in such applications, we see that the unbalance may be present in multiple rows, because multiple rows contain multiple blades, and therefore for each blade we should take it one by one, and that's what is shown here. So schematically, if I were to represent this situation, you have the shaft which is shown by this black line, which is mounted on the bearing, and here I have just shown 3 blades. Each of these rows of blades could bring in a certain eccentricity, the red one, the blue one, and the green one. And again, the orientation between these rows could be perfectly arbitrary. The red, green and blue could have perfectly arbitrary orientation. Now, how to detect these things and how to experimentally find out that what are the individual unbalances is a topic which is very interesting in its own right, and something that definitely you should look for to understand. But unfortunately, the curriculum permits, first the curriculum at this stage does not permit such a discussion. Rather, you would have to pose the opposite question, that suppose I know that these are the unbalances created at the individual rows, how do I handle this situation? Now, that supposition of how do you estimate the unbalances in the field, or even through some additional reading, you can find out how exactly you can estimate these unbalanced forces. That can be done through some advanced experimental techniques. But once someone tells you, fine, this is the unbalance in row 1, this is the unbalance in row 2, this is the unbalance in row 3, and this is how the individual unbalances are getting aligned. Now tell me, what is your design solution such that my structure is totally balanced, right? So this second part of the problem is what we will study through our present curriculum. So the first question as to how to estimate these unbalances is not possible at present, but I definitely encourage you to read some additional material in the literature which will have these. For example, the book by Ghosh and Malik, which is given in the reference, is having a lot of discussion about how balancing machines are used to estimate unbalances. So there is a very exorbitant discussion on that. So you can read that for a startup, but yes, there are more advanced techniques also than that is presented in that book. So I recommend you to do that. But at present, as I said, assuming that we know the unbalances, we will try and find the solution to these unbalances. So as we said, in static unbalance, what is happening is that the rotating disc always has a preferred configuration in terms of static equilibrium. Now consider this situation wherein you just have 2 unbalanced masses at 2 different locations, but just fortuitously, just matter of luck, these have been arranged in equal and opposite fashion. Now what will happen in this case is that this system will have no preferred orientation in static equilibrium. Each orientation is as likely as the other. So therefore it is statically balanced, but dynamically it is unbalanced, because each of these equal and opposite forces, the red and the blue one, is going to lead to no unbalanced forces, but again unbalanced moments. And to get rid of that unbalanced moments, as I said, again the bearing reactions will have to kick in, and that will in turn lead to shaking forces getting transmitted onto the frame structure. So these forces are balanced, there is no preferred static equilibrium configuration, and therefore the system is statically balanced. But then this is where, as I said, that the bearing reactions will be equal and opposite, because force equilibrium is ensured, moment equilibrium still has to be satisfied, so bearing reactions are still induced. So this is in contrast to dynamic unbalance, as in in contrast to static unbalance, this is the situation of dynamic unbalance, where in static unbalance that can be easily detected because there is a preferred static configuration, whereas in this system there is no preferred static configuration, it cannot be that easily detected, but as I said, it can be detected as well as estimated through more advanced experimental techniques which lies beyond the scope of current discussion, but you should definitely read it for your own sake. But none the same, at this point what I wish to emphasize is that this is the situation of dynamic unbalance as opposed to static unbalance. Static unbalance can be detected by a static test, whereas dynamic unbalance has to be detected by more advanced techniques which is possible in a balancing machine. So at present what we will try to do is how to handle the situation of unbalance once it is estimated. So now let us get back to our problem of multiplane unbalancing. So all unbalanced forces, so the claim is the following, that no matter how many unbalanced forces are there in your rotating shaft system, all of them can be killed by simply putting two unbalanced counter masses. So if you put two counterbalances within your rotating shaft system, everything will get killed. So before doing the problems associated with that, let us build some conventions as to how to do this problem. So here we have a free body diagram of the rotating shaft. So this rotating shaft in front view carries two unbalances as is shown, but the unbalances have different orientation which will be visible if you take the side view. So in side view you get to see that this is the two unbalances, and the centrifugal force associated with each of these unbalanced forces definitely gets aligned to the unbalance itself. So the orientation of the centrifugal force is exactly coinciding with the orientation of eccentricity as we talked in the case of single plane unbalancing. But now we have to care about another issue which is that of moment. So to estimate moment, again we have to arbitrarily select a reference about which the moment will be calculated. So this is the dotted line represents that reference about which we are going to do the moment calculations. Now the unbalance which is lying towards the right of this reference plane will create a moment which is given by the cross product of this vector multiplied by this vector. So it will take a while for you to visualize that this r cross f will be along this direction on the left side view, whereas if this is the unbalanced force and the position vector from the reference plane is denoted by this blue arrow, this r cross f will lead you to an unbalanced moment which is now pointing in this fashion again in the side view of it. So please understand that the forces associated with the unbalance is exactly aligned with the direction of the unbalance, whereas the moment should be 90-degree should make a 90-degree angle with the forces. But you will observe, whereas the moment in the red case is 90-degree in the clockwise sense, the moment in the blue case is 90-degree in the counterclockwise sense. So the direction, the angular orientation between the force and moment is 90-degree, all right, but it changes if you are taking a plane which is to the right of your reference plane, or if you are considering the unbalanced plane which is to the left of your unbalanced plane. So the convention that we will have to take up, we must understand, is because of this, that the moments are not definitely aligned in the same fashion throughout. The moment due to the unbalanced forces which lies to the right of the reference plane will be 90-degree clockwise, whereas the moments due to the unbalanced forces which are on the left of the reference plane is 90-degree counterclockwise. So the sense of this 90-degree rotation between the force and the moment is exactly opposite depending upon whether the unbalanced plane is on the left or right. So we have to make some conventions so that our life is made simpler and we don't have to keep taxing ourselves with this visualization time and again. So that is what we are going to do in the next slide. So for the force, everything is nice and simple. Force vectors are along the direction of unbalance. If we know what is the direction of eccentricity, we will directly get the direction of the force vectors. Moments are calculated about the reference plane. The choice of reference plane is completely arbitrary. Whichever reference plane you want to choose, you can choose. But again, in practice, it will turn out that there is a smart choice of reference plane which will enable you to make calculations in a very fast fashion. So that we will come to when we will take up the problem tomorrow. As we have observed, moment vectors are rotated counterclockwise in the left side view. Moment vectors to the right of the reference plane are aligned to the unbalance, whereas moment vector, so now what we are going to do is the following. These dotted lines represent the actual moment vectors, right? So what we are going to do is that we are going to rotate all the moments by 90-degree counterclockwise. So when we make a 90-degree counterclockwise rotation as per the convention, we will ensure that this red moment, the moment due to the red unbalance, will exactly get aligned with the unbalanced vector itself, or with the force vector itself. Whereas the blue vector, if I give a further 90-degree counterclockwise rotation, the moment vector will be opposite to the unbalanced vector. So that is my convention. I will not try to look at the actual moment, but rather I will try to look at the rotated moment, moment which is rotated 90-degree counterclockwise. And the reason why I am adopting this convention is that if I look at the rotated moments rather than the actual moments, the moments due to the unbalance which are to the right half of my reference plane will get aligned exactly with my unbalance, just like the force. The force, the unbalance and the moment all will be pointing in the same direction. Whereas the moment which is located on the left side of my reference plane will be opposite to the direction of unbalance in the direction of the unbalanced force. So that will be very helpful for me in the bookkeeping, and also in case I wish to draw, it will be very helpful. So I will not calculate the actual moment, rather I will calculate the moment vectors which are rotated by 90-degree counterclockwise. And remember, it's 90-degree counterclockwise in the left side view. So we are strictly obeying the first angle projection. The view that is presented to the right is the left side view, which we are getting to see if we look from this side. So with that convention, we are able to find the moment vectors with a pi by 2 counterclockwise, and moment vectors, as I said, to the right will be aligned along the unbalance, and moment vector to the left will be aligned opposite to it. This is perfectly reasonable, because all that we want is summation of force should be equal to 0, summation of moment should be equal to 0. This is the criteria that we are looking to satisfy. So instead of looking at summation of actual moments to be 0, we are looking to satisfy summation of rotated moments to be equal to 0. This is both the criteria are completely equivalent. If in a certain system you have summation of actual moments to be equal to 0, for the same system summation of rotated moments is also equal to 0. So whether I take the moment as it is or I take a rotated version of the moment diagram, the equilibrium condition is actually not changed. And since my purpose here is to ascertain what are the masses such that I should put in my two planes, such that I should have summation of all forces to be 0, summation of all moments equals to 0, the fact that I am rotating the moments is not going to cause any hindrance, because if the rotated moments lead to a summation 0, the actual moments equivalently lead to a summation 0. So there is nothing criminal that I am doing at this stage by rotating my moment vectors. The moment vectors can as well be rotated, and you can impose the equilibrium condition on the rotated moment vectors rather than the actual moment vectors. So with that, we can draw the force and moment diagrams in this fashion. So here we realize that the red and the green are on the right side of my reference plane, whereas the blue is on the left side. So the unbalanced orientation is as dictated here. So the force diagram is very simple. The force diagram will have the orientation, each of these unbalanced forces will have the orientation exactly as the unbalanced forces. Whereas in case of the actual moment diagram, these forces will be rotated by 90 from the forces. Those which are on the left half of the plane will be rotated 90 clockwise. So if you observe the force, the red force here and the red moment here, it is a 90 clockwise rotation. Similarly, the green force here and the green moment here is a 90 clockwise rotation. Whereas in the blue case, it's a counterclockwise rotation. The blue force and the blue moment, it's a counterclockwise rotation. So instead of working with this moment diagram where you always have to remember clockwise, counterclockwise, and there's a chance that we might confuse ourselves with, instead of looking at this diagram, I look at the rotated moment diagram. The rotated moment diagram is the one which I rotate this entire diagram by a 90-degree counterclockwise. So when I am doing that, I rotate this entire piece 90-degree counterclockwise, it looks in this fashion. And now what I get to see is that my moment for those unbalances which are in the right of my reference plane is exactly aligned to the forces. The moment for the red and the green is exactly aligned with the forces. The moment which is on the left for the left unbalance is exactly opposite to the force. So in the rotated moment diagram, the convention is easy. The moments which are on the left of the reference plane will have the alignment opposite to the force, whereas the moment which is to the right of the reference plane will have an alignment equal to that of the force. The force itself is always aligned with the direction of unbalance. So with that, we are in a very happy situation, and hopefully our confusions and bookkeeping will be much easier in this form. So remaining what we have to do is that we will now put two unbalances in planes 0 and n. Suppose we have the actual unbalance in the machine in planes 1, 2 and n. Each of them by magnitude are given by this, and the by orientation is given by this. So the problem of two plane balancing is follows. We have to put two unbalances 0 and n with m0 e0 and mn plus 1 en plus 1 such that the summation of all forces and the summation of all moments after this addition satisfies both force and moment equilibrium conditions. This is what we will do tomorrow. I don't want to rush you through in this. So we will take it up from here in two plane balancing when we meet tomorrow, but I hope you get this part clarified, that why we are adopting this convention of rotating the moment vectors. It is simply to make our life simple. It is not to confuse you that we are adopting the convention. In fact, to make sure that you don't get confused with the directions of moments, we are adopting this convention. So we will make good use of this convention tomorrow when we meet, and we will try and solve some problems also to settle this matter. At present, for the 5 minutes time that is remaining, I will make myself open to any questions and interactions you would like. Please feel free to ask any questions on today's lecture material, or something which is related to it also is welcome. Concept of balancing in V engines. We are far away from V engines now. We are doing rotary balancing. So please limit your discussion to what has been asked. In fact, V engine is not even within the topic of the syllabus for 6 hours. It will make sense if you understand single plane, single cylinder engines, then inline engines, V engines will automatically come. So don't worry about things which are not talked about. Let's keep our discussion to what has been talked about. Yeah, DGI, please go ahead.
Hello.
Yep.
Yes. Hello.
Yes.
Hello. Good morning, sir. Sir,
Good morning.
you have made. Yes, sir. You have made a 90-degree rotation to the actual movement diagram,
Yes.
right?
Right.
So, question is, what was the ease that you get in balancing from that 90-degree rotation of movement diagram?
There is no ease in terms of balancing. The balancing conditions exactly the same. All that I am trying to do is arrive at my force and moment vectors very quickly, because otherwise I will always have to look at the cross product and arrive independently at the direction, and forever there is a confusion whether it is 90-degree plus or 90-degree minus. I am trying to resolve that confusion by looking at the rotated moment vector diagram. In terms of balancing, you are correct. It is nothing. It is just an interchange of cos theta sin theta. Basically, if you look at it that way. So if you don't adopt this convention, instead of taking the x component as cos theta and y component as sin theta, you have to take the x component as sin theta in the moment diagram and the y component as cos theta in the moment diagram. So in the force diagram, the components would be x and y would be cos and sin, whereas in the moment diagram it will be the other way around. So that can be actually more confusing in the for the field engineers and for the practicing engineers. So therefore we are adopting the rotated moment diagram, wherein after the rotation, everything will have the same components. The rotated moment diagram will have again same cos sine component between the force and the moment. All it is a perfect alignment. That's why we are rotating it. Have I answered your question?
Yes, sir.
So it's just a matter of ease. That's all. For pen and paper calculations, it doesn't matter. You can do the calculation without rotation also. Yeah. Any other questions? PSGCT, you're asking how balancing is done in fluid couplings. I don't think that is within the topic of discussion. Please look at the literature if you want to, but typically in a dynamics of machines course, that is not what is expected to be talked about. Okay, CEC is asking which designs are supposed to minimize unbalanced forces as told in the objective. Presently, we have looked at only single plane balancing, rotary balancing in the context of rotary balancing. So there is minimum we had discussed. So hopefully within the 3 sessions we should give you some designs which are better than the other. But you can't say this is the best design as always. There is always a better design that is possible. I think the objective that you guys should be looking for is to understand what is unbalancing, and if the unbalance is known, how do you arrive at a balancing condition. That is the objective, and if you look at that objective rather than thinking about too many things at this point, you will be helped in this lecture material. Okay, if there's no questions, then it's time to say goodbye. So tomorrow when we come back, we are going to do a problem in two plane balancing, and we are going to see how nicely it can be implemented. After that, we will move on to balancing of reciprocating machines, and there, as I said, we are going to talk principally in the context of IC engines, which is having the piston as its reciprocating part. So the a revised version of the presentation then that has been uploaded in your course pack will be made available to you. You will probably realize that there is a revision in this diagram. This diagram was incorrect in the handout that if you are having is probably incorrect. So that is revised in the presentation material that you are now seeing. So I'll make that revision and again upload it in the course pack. So have a good day ahead, and I hope your life is balanced and you don't suffer from any unbalanced forces and moments. With that, thank you very much.